Okay. So give me just a second. Okay, so I've started recording. That's good. So let us quickly understand where we are. So we have taken the fundamental commutation relations of the generators of angular momentum Ji, Jj is IH bar epsilon ijk jk, and the fact that excuse me, j square, which is ji commutes with any other rotation generator, right? So just armed with these two facts, we have been able to understand the structure of the Hilbert space in which these j's reside. In particular, we started with the eigenvalue equations for j square and jz, and we actually showed that the eigenvalue of the j square operator is h bar square jj plus 1, and the eigenvalue of jz is mh bar times the same eigenkets, where jm are the simultaneous eigenkets for j square and jz. Excuse me. And m, we show, can range from minus j to plus j. Okay, totally 2j plus 1 values, because 0 is also counted. So that's why you have the plus 1. And we also showed that m has to be an integer or a half integer. Okay, so j has to be an integer or a half integer, right? So j equals 0, 1 half, 1, 3 half, blah, blah, blah. Okay, now the question is, what is the J matrix? Now, to understand what the J matrix is, we can understand what the J square and Jz matrices are for certain spin cases. Okay, but nobody here tells me at this point that I'm talking about a J equal to 0 system or J equal to 1 half system. So I need to be able to construct the entire J matrix corresponding to all the different possible J values. Now, we will postpone this discussion to about one lecture or so, where before I introduce certain things like direct sum and direct product of Hilbert spaces, vector spaces. Okay, so direct sum and direct product are basically means by which you can construct larger vector spaces out of smaller vector spaces. So when I say larger or smaller, I mean the dimensionality of the Hilbert space. Okay. So if you give me an n-dimensional Hilbert space and an m-dimensional Hilbert space, there is a way in which I can put together things and create an n plus m dimensional vector space. Okay, so such a vector space is called a direct sum of these two vector spaces. And there is also a way in which I can construct a new Hilbert space whose dimensionality is n times m. So that is a direct product or a tensor product of Hilbert spaces. We will develop these concepts with some simple examples. But before getting into that, let us take a very practical example and work out these J matrices. I will work them out in the class for the J equal to 1 half case. So J equals 1 half. Okay. Oh my gosh. So just give me a second. I'll check. Okay. So J equals 1 half. In fact, we will show when we talk about addition of angular momentum that there is only one way in which this can be constructed. And this can be constructed by adding an L is equal to 0 state with an S is equal to 1 half state. Okay. The other possibility, S is equal to 0 and L is equal to 1 half does not exist because L cannot take half integer values. Okay. So this is a pure spin case. So in some sense, it is intrinsically just a spin quantum number. Anyway, so regardless of where it comes from, let us put together the basic skeleton of what we have. So since J is equal to 1 half and M can go from minus J to plus J in intervals of 1 unit, there is only two possible values of M you can take in this case. So M can be equal to minus half or plus half. Okay. Remember that M goes from minus J to plus J in increments of 1 unit. Okay. So this is actually a two-dimensional Hilbert space. Okay, and the two vectors, the eigenkets that span this Hilbert space, the JMs, are J equals 1/2 and M equals 1/2, and J equals 1/2 and M equals minus 1/2. Okay, so these are the two eigenkets. So when I say that these span the Hilbert space, I mean that these are orthogonal. So remember that Jm prime is delta M prime. This is true because M and M prime are the eigenvalues of a Hermitian operator Jz. So eigenkets corresponding to different eigenvalues of a Hermitian operator are actually orthogonal because of our general theorem. So writing this out explicitly, we have 1/2 overlapped with 1/2 is equal to 1/2 minus 1/2 overlapped with 1/2 minus 1/2. These are both equal to 1. And the overlap of 1/2 with 1/2 minus 1/2 is 0. Okay, so this is what the above equation means when you write it out explicitly. Okay, so now we want to understand how the matrices for J square, Jx, J1, J2, J3 all look like, or Jx, Jy, Jc. But I think I have used consistently J1, J2, J3. So, and I made a slip here. So I'll call this J3. All right. So let us start with J square and J3 because they are simple. J square and J3 are actually very simple matrices in this Hilbert space because Jm are already the eigenvectors of J square and J3. So in other words, J square acting on 1/2 is h bar square times J into J plus 1, which is 1/2 into 1/2 plus 1 times Jm. Okay. And similarly, J square acting on 1/2 minus 1/2 is also the exact same eigenvalue because J doesn't care about what M we are talking about. So this is equal to, this is what, 3/4, right? One half. Similarly, J square acting on 1/2 minus 1/2 is also the same thing. 1/2 minus 1/2. This is so because 1/2 and 1/2 minus 1/2 are eigenkets of J square operator. So when I say what are the matrix elements of J square, what do I mean? I am looking for the elements 1/2 J square 1/2. This is the 1 element. 1/2 J square 1/2 minus 1/2. This is the 1 element. 1/2 minus 1/2 J square 1/2. This is a 2 element. And as you can guess, this is the 2 element. Okay. So this is, for example, EI J square EJ equals JIJ. These are the matrix elements, and this is, if you put together all the matrix elements, you develop the entire matrix for J square. Now, how is this matrix going to look like? You already know that this is going to be a diagonal matrix because we are expanding it in the eigenkets of J square. So by definition, if you expand something in the eigenkets of a particular matrix, you're going to get a diagonal matrix. That is the very essence of diagonalization of a matrix, right? So plug in everything. So for example, if you evaluate 1/2, J square 1/2 minus 1/2. Now J square acting on 1/2 minus 1/2 is going to give you 3/4 H square times. And since these are orthogonal eigenkets, this is equal to 0. So the off diagonal elements are going to be 0. So in this basis, the matrix for J square will be 3/4 H bar square 1 0 0 1. I'll put a box there because this is our first result for the spin half case. At any point, if you have any questions, please do unmute and ask. Okay. So now let us ask what is the matrix for J3 in this basis. Again, since these are eigenkets for J3 also, the J3 operator is also going to be a diagonal matrix, but let us verify. Again, J3 is going to be the matrix J3, 1/2, 1/2. J3, 1/2 minus 1/2. I'll write this out explicitly just for this case, and then I will use a symbolic notation for the J1 and J2 operators. Okay. So using the fact that J3 acting on 1/2, 1/2 is m h bar, m for this state is 1/2. So it is h bar over 2, 1/2, 1/2. And J3 acting on this state is m here is minus half. So this will be minus h bar over 2. Okay. So use this fact and evaluate these matrix elements explicitly. So for example, 1/2, 1/2, J3, 1/2, 1/2 would be equal to J3 acting on 1/2, 1/2 will be h bar over 2 times 1/2, 1/2. So this can be evaluated as overlap of 1/2, 1/2, which by our definition is just 1. So this is h bar over 2. Okay. If I look at any off diagonal element like 1/2 minus 1/2, J3, 1/2, 1/2, this is going to be equal to h bar over 2. Again, J3 acting on this guy is going to give me the same thing. And this will be the overlap of the orthogonal eigenkets, and this will be 0. Okay. So the J3 operator or matrix in this two-dimensional Hilbert space constructed out of the eigenkets of J3 and J square is going to be a diagonal operator, diagonal matrix with entries 1 and minus 1. Okay. So these two, since these are the explicitly the eigenkets of J square and J3, you expect J square and J3 to be diagonal, and this can be simply evaluated. To evaluate or to figure out how J1 and J2 look in this Hilbert space, we have to do a little bit of work. Okay. So before I move on, are there any questions about the J square and the J3 matrix? So I did this out quite fast, but if this is the first time you're seeing this, please take your time to work this out. Don't take things for granted. Work every step out and then make sure that they get all the plus and minus signs right, because getting plus and minus signs right would be crucial in these calculations. Okay. So let us evaluate, let us compute the J1 matrix in this two-dimensional Hilbert space for the J is equal to 1/2 case. So what is J1? Again, I directly don't know how J1 acts on the Jm states, but I do know how a linear combination of J1 and J2 act. In particular, I know that J plus Jm is square root J plus 1 minus M, what was it? M minus 1 or plus 1? I forgot. So M plus 1 minus M plus 1, J M plus 1, and J minus acting on this would be J plus 1 minus M minus 1 acting on J M minus 1. Okay. So J1 is just 1/2 of J plus J minus. Okay. So to understand what J1 is, I need to be able to understand how J1 acts, J plus acts on the states and J minus acts on the states. So let us evaluate the matrix elements of J1 operator. In particular, let us evaluate 1/2, 1/2, J1, 1/2, 1/2. Okay. This will be equal to 1/2 of, this is J plus J minus 1/2, 1/2. Okay. So for shorthand, I will call the this one as C plus and this one as C minus. Okay. I will evaluate this, but if I don't need to evaluate, I'll just use shorthand. So this is equal to 1/2 C plus 1/2, 1/2. J plus acting on 1/2, 1/2 is going to give me 1/2, 1/2. Remember that, okay, so actually let me evaluate this explicitly so there is no confusion. So J plus acting on 1/2, 1/2. What is this going to be? Remember that we are already in the state with maximum value of M. So remember that for J is equal to 1/2 case, the maximum value of M is +1/2 and the minimum value of M is -1/2. And it so happens that these are the only two values possible in this Hilbert space. So we are already in the maximal states, which means J plus cannot act on 1/2, 1/2 because if it acts, it cannot possibly increase the M value further because the M value is constrained by the J value. So J plus acting on 1/2, 1/2, as you know, is 0. Okay. Similarly, J minus cannot reduce the value of M to be less than -1/2 because otherwise I'll go below minus J. So this also equals 0. Okay. Now J plus acting on 1/2 minus 1/2 is possible because this increases the value of M by 1 unit. So -1/2 plus 1 is 1/2. So this will be proportional to the state 1/2, 1/2. Similarly, J minus can reduce the maximum value of 1/2, 1/2, and this will be proportional to the state 1/2 minus 1/2. Okay. So let us actually work out the proportionality constant also, since we are doing this out completely. So this is equal to square root of J into J plus 1. Sorry, there is also an H bar somewhere here. Right? So there is H bar, which I forgot. Okay. So this is H bar J into J plus 1, which is 1/2 into 1/2 plus 1 minus M into M plus 1. So minus M here is -1/2 because it is acting on the state -1/2. M into M plus 1, 1/2, 1/2. Okay. So what is this equal to? So this is equal to H bar. So this is 3/4. So this is 1/2 and this is another 1/2. So this is 1/4. So this is H bar times 1/2, 1/2. Okay. Similarly, let us calculate J minus acting on 1/2 minus 1/2. So this is again H bar square root of J into J plus 1 minus M into M minus 1. So J minus of this plus half minus M into M minus 1. So 1/2 minus 1, 1/2 minus 1/2. So this is equal to H bar. This is 3/4, same as before, and this is again 1/4. Minus half minus half plus 1/2. So this is H bar acting on 1/2 minus 1/2. Okay. So knowing how J plus and J minus act on these basis, we can construct the matrix elements for J plus or equivalently the matrix for J plus or equivalently the matrix for J minus. So let us do both. So what is the matrix for J plus? So 1/2, 1/2, J plus 1/2, 1/2 is 0 because J plus cannot act on 1/2, 1/2 to raise it further. 1/2, 1/2, J plus 1/2 minus 1/2 is, now J plus acting on 1/2 minus 1/2 is, as we just discussed, H bar times 1/2, 1/2. So this will be equal to H bar. Now coming to the other one, 1/2 minus 1/2, J plus 1/2, 1/2 is again 0 because J plus cannot raise the value of M higher than 1/2. And 1/2 minus 1/2, J plus 1/2 minus 1/2 will be 0 because J plus acting on 1/2 minus 1/2 will give me 1/2, 1/2, and the overlap of 1/2, 1/2 with 1/2 minus 1/2 is 0. Okay. So the J plus operator has a matrix form which is H bar. The 1, 1 element is 0. The 1, 2 element is 1. the 2, 1 element is 0 and the 2, 2 element is also 0. So J plus will necessarily be off diagonal. There will not be any diagonal elements because J plus changes the M value. So if you have any questions, please ask. Now let us go to J minus. 1/2, J minus 1/2 will be equal to 0 because J minus acting on 1/2 will give me the other orthogonal state 1/2 minus 1/2. 1/2 J minus 1/2 minus 1/2 will also be 0 because J minus cannot act on 1/2 minus 1/2 to reduce it further. So 1/2 minus 1/2 J minus 1/2, the 2, 1 element. This will be non-zero because J minus will act on 1/2 minus 1/2 to give me 1/2 minus 1/2, and the overlap of it with the same state will be 1. So this will be H bar. And this will also be 0 for the same reason as before. J minus cannot reduce the value of M to be less than minus 1/2. This looks like that. So the J minus matrix in the 1/2, 1/2, 1/2 minus 1/2 Hilbert space, basis vector space would be equal to the 1, 1 element is 0, 2, 1 element is 0, sorry, 1, 2 element is 0, 2, 1 element is H bar, and 2, 2 element is 0. Okay. Are there any questions about how the J plus and J minus matrices look like? So now that I know what J plus and J minus look like, I need to just take linear combinations of these matrices to give me J1 and J2. So J1 is 1/2 of J plus J minus. So this is equal to 1/2. So there is both H bar. So there is an H bar for both these matrices. So I'll take the H bar out common. So this is H bar over 2 times J plus, which has a 1 in the 2, 1 element, and J minus, which has a 1 here. So this is equal to, so this tells me that J1 equals H bar over 2 times the addition of these guys gives me 0, 1, 1, 0. Okay. So for people who know the Paoli matrices, a familiar form should be emerging. Okay. So J3 is this and J1 is this. So for completeness sake, let's also finish out J2. J2 is 1 over 2i J plus minus J minus, right? Because J plus is J1 plus ij2 and J minus is J1 minus ij2. So if I subtract these two, J plus minus J minus, I get 2ij2. Right? So J2 would be 1 over 2i times the difference between these two matrices. So this is, and since both J plus and J minus have an overall factor of H bar, I'll take the H bar out common, H bar over 2i, J plus, which is 0, 1, 0, 0, minus J minus, which is 0, 0, 1, 0. So this is equal to H bar over 2i times 0, 1, minus 1, 0. Okay. So which tells me that J2 can be written as H bar over 2 times 1 over I is minus I. So if I multiply it throughout by minus I get 0, minus I, 0. So J plus is purely, sorry, J minus is purely imaginary. Excuse me, J2 is purely imaginary. Okay. So these matrices, forgetting the factor of H bar over 2, these matrices have a special name and they're called they're named after the famous scientist Wolfgang Pauli. These are the Pauli matrices. So sigma 1 is 0, 1, 1, 0. Sigma 2 is 0, minus I, 0. and sigma 3 is 1, 0, 0, minus 1. Okay, they actually come from the explicit application of the angular momentum algebra. So the Ji for the spin 1/2 case is simply h bar over 2 times sigma, the 3 Paoli matrices. Okay. So you can similarly work out the J representation for example, the J equal to 1 case. J equal to 0 case is trivial because there is only one basis vector, which is J equal to 0, M is equal to 0, right? So there is no question of any other operator in this Hilbert space because there is nothing for this state to change into. There is only one state overall in the Hilbert space. Okay. So, so for completeness sake, let us actually have a little more fun with Pauli matrices. But before I move on, are there any questions about any of this? Okay. So I will ask you to work out the J equal to 1 representation in your tutorial. So again, J equal to 1 should be similar. J equal to 1. So what is the dimensionality of this Hilbert space? The dimensionality is 2J plus 1, which in this case is 3, because J is equal to 1, right? For J equal to 1/2, 2J plus 1 is 2. That's why we had a 2-dimensional Hilbert space. Okay. So the vectors are, you can think of them as column matrices if you want, and the operators in this 2-dimensional Hilbert space are 2 by 2 matrices, the Pauli matrices. So the J equal to 1 case, you'll have 3 basis vectors. What are the basis vectors? The Jm vectors in this case would be J equal to 1 can correspond to an M value of 1, can correspond to an M value of 0, can correspond to an M value of -1. That is all, nothing else, because M cannot be greater than plus J or less than minus J. So there is only 3 vectors possible, and you have to work out the matrix elements of J1, J2, J3 in this 3-dimensional vector space. So you'll have to work out things like 1, 1, J1, 1, 1, 1, 1, J1, 1, 0, and so on and so forth, right? So do it methodically, just like we have done it for the J equal to 1/2 case. And in this case, the J should be 3-dimensional matrix, so 3 by 3 matrices. So you figure out what J1, J2, and J3 are for this 3-dimensional Hilbert space. Okay, so we'll do it methodically. You will get the answer correctly. We'll also revisit this in the tutorial.
Hello, sir.
Yes.
Sir, which will be the one element with whether it will be a 1 minus 1 J1 1 minus 1 or 1 J1 1 minus 1 1.
So it doesn't really matter. You have to arrange it and be consistent with it. So the notion that is usually adopted is, so arrange it in this fashion. So this is 1, 1. So go down in M value like this. Okay.
Okay, sir.
1, 0, 1, minus 1. Okay. So the first element would be the overlap of 1, 1, J1 with 1, 1. The 1, 2 would be the overlap of 1, 1, J1, 1, 0. And 1, 3 would be 1, 1, J1, 1, minus 1. And just like that. So fill up this. Okay.
Okay, sir.
Any other questions? Okay. So I will erase this because we are not going to do this now. But for completeness sake, I'll also talk about finite rotations in the case of J equal to 1/2. So what would be, so remember that all this corresponds to infinitesimal rotations, right? So the whole algebra of the whole commutators arise because we are talking about infinitesimal rotation. So what would be a finite rotation for the J equal to 1/2 case? So how to construct the finite rotation operator? We already discussed this. For translation also, we discussed this. So suppose if I want to rotate it by some general angle theta, which I can write as u of theta in some direction n hat. Okay, this could be any direction in the 1, 2, 3 space. I don't know what this is. This is not the XYZ space. Again, remember that I'm doing a rotation in a different Hilbert space, in an internal Hilbert space specified by the 3 directions 1, 2, and 3. Okay, so what would such a rotation look like? Now again, I'll have to write this as limit n goes to infinity, 1 minus I over h bar n theta dot j to the n. Okay, and this limit can be evaluated just like we evaluate the limit for the translation operator, finite translation operator, and u of theta can be worked out to be e to the minus I over h bar theta dot j. Okay, so if you're confused by this, please go back and look at the corresponding calculation for the translation operator that we did, and you'll get the exact same. In general, this is where we should stop if we are talking about, so what is this j? It depends on whether you're talking about j equal to 0, j equal to half, j equal to 1, and j equal to 2, or things like that. In general, remember that since j's are matrices, exponential of a matrix is also a function of matrices, so you should be able to get a closed form for this u. But in general, except for some very simple values of j, it is very hard to get a closed form for this u, but we can work out the closed form for small values of j. So let us look at what this matrix looks like for j equal to 1/2. For j equal to 0, it is trivial, it is just 1 because there is no rotation possible. There is only one state, there is nothing to rotate it into. But for j equal to 1/2, there is two different possible states, and we know what the j matrices are. So for j equal to 1/2 case, we know that this ji is h bar over 2 sigma I, the Paoli matrices. And Paoli matrices, as you have discovered in your tutorial problem, have some remarkable properties. Sigma I, sigma j plus sigma j, sigma I. The symmetric combination of such a product is equal to 0 if I is not equal to j, and is equal to 2 if I equals j. Okay, this also told you that sigma I square is just the unit matrix 1, 0, 0, 1. Okay, so on and so forth. So we can use these properties of sigma to actually evaluate this u of theta in a closed form for a finite rotation just for the j equal to 1/2 case. So let us evaluate this explicitly. So u of theta for j equal to 1/2 is e to the minus I over h bar. Theta dot j can be written as theta I ji. But for j equal to 1/2, ji is just h bar over 2 sigma I. So this is e to the minus I over h bar theta I h bar over 2 sigma I. The h bar cancels, and this is equal to e to the minus I over 2 theta I sigma I. Okay. Now, theta I is the is actually a vector the way I have defined this. But instead of writing theta vector, I will write this as the absolute value of theta vector, which is theta, the actual amount of angle by which I rotate, times the unit vector in some direction n. I don't know what the direction is, but it is some unit vector n cap. So I will write this as minus I over 2 theta ni sigma I. Okay. What is ni? Ni is some direction. I don't know what direction it is. Ni is a unit vector such that ni dot nj is delta ij. Okay, so they define some orthogonal unit vectors in this Hilbert space. So I'm going to evaluate this. I'm going to evaluate this by, it turns out that this actually can be evaluated in a closed form for the j equal to 1/2. And the way I would do it is by expanding out the exponential completely. So I'll write down various different terms. Remember that sigma is a matrix. So if I expand this exponential out, each term would be a matrix. So I'll write this as, the first term is obviously 1 minus I over 2 theta ni sigma I plus 1 over 2 factorial minus I theta over 2 whole square ni sigma I whole square plus 1 over 3 factorial. I'll write down a few terms so you see a pattern emerging. Minus I theta over 2 cubed ni sigma I cubed plus 1 over 4 factorial ni sigma I whole 4 plus blah blah blah. Okay, I'll stop here because this is enough. Now this looks like a very difficult thing to do because we don't know what ni is. I don't even know which direction I'm rotating around. But it turns out that I can actually evaluate this surprisingly in closed form. The reason is as follows. True, I mean, whatever I do, finally I should get some function of Ni because it should specify a rotation around some direction Ni. But it turns out that this products of Ni sigma I can be actually evaluated. How? Because this can be written as Ni sigma I times Nj sigma j. Okay. Now n is a unit vector, so Ni Nj is some symmetric combination of I and j. So I can write this as Ni Nj, and since Ni Nj is symmetric, only the symmetric combination of sigma I sigma j will survive in this sum. So I can write this as 1/2 sigma I sigma j plus sigma j sigma I. Because anything antisymmetric in sigma I and sigma j will not survive when I sum over I and j. Okay, but I know precisely what the symmetric combination of sigma I and sigma j is. This is the special property of sigmas I was referring to. So this is basically 12 delta ij. Okay, so this is equal to Ni Nj times 1/2 times 2 delta ij, which is Ni square. But since this is a unit vector, the length of this unit vector is 1. So this is just 1. Similarly, we can show that, for example, Ni sigma I cubed can be written as Ni sigma I square times Ni sigma I, and Ni sigma I square is just 1. So this is just Ni sigma I. So any odd combination of any odd power of Ni sigma I is just Ni sigma I, and any even power of Ni sigma A is just 1. 4. So excuse me. 4 is Ni sigma I square times Ni sigma I square, which is 1 times 1, which is 1. So this exponential only has two different classes of terms. The first class of terms, which is proportional to the identity matrix 1, and the second class of terms, which is proportional to the Paoli matrix sigma I. So plug this in, and you will find that u of theta, finite rotation for the spin half case, is the first term is 1. I will write it as a matrix 1, just to be clear. The second term is minus I theta over 2 Ni sigma I. The third term is 1 over 2 factorial minus I whole square is minus 1, right? So this is minus 1. Theta over 2 square. Ni sigma I square is just 1. So this is times 1. The third term is, what is minus I cubed? Minus. So this is minus 1 over 3 factorial minus I cubed is minus I square times minus I, and this guy is, sorry, this is plus. Okay? Yeah, this is plus. Sorry about that. Theta over 2 cubed Ni sigma I. And the fourth term, just to finish it off, is minus I to the 4th, which is minus I square minus I square. This is plus 1. So this is plus 1 over 4 factorial theta over 2 to the 4th times 1 minus so on and so forth. So I can write this, I can collect all the unit matrices and I can collect all the sigma i's. I can write this as 1 minus 1/2 times theta over 2 square plus 1 over 4 factorial times theta over to the 4th minus so on and so forth times the unit matrix minus I times theta over 2 minus, so there's a minus of I over here, theta over 2 cubed plus blah, blah, blah times ni sigma I. Okay. So as you can see, the first square bracket is just the expansion of cosine. The second square bracket is just the expansion of sine. So for a finite rotation, for the spin half case, the finite rotation operator is nothing but cosine theta over 2 times the unit matrix. Did I make a mistake here? No, as far as I can see, this is correct. Okay, minus I sine theta over 2 times ni sigma I. Okay, so it turns out that just for the case of j equal to 1/2, one can actually develop closed form representation for the finite rotation operator, which might not be possible for higher spin representation. Okay, so I'll finish this discussion tomorrow, and then I will introduce you to the notions of direct sum of linear vector spaces and direct product of linear vector spaces. We don't have time for that now, so we'll stop here for today. And tomorrow we will continue with this discussion. We will finish off this discussion and introduce certain notions about linear vector spaces. Okay.